Hi, thank you for visiting my presentation on codependence measures and tools with MLFinLab package. First, let me introduce myself. My name is Illya Barziy, and I am a quantitative researcher at Hudson and Thames Quantitative Research. I've recently graduated from University of Warsaw and got my master's in computer science and econometrics. Over the last 6 months, I've been working on developing the MLFinLab package, and I will be showing you its capabilities today. These are links to my GitHub and Twitter account if you would like to discuss some details about the presentation, or you may have some propositions. I will be glad to discuss these propositions with you there. So first, I'm going to cover the MLFinLab package and Hudson and Thames. Then I'm going to briefly cover the functionality of the MLFinLab package and show you where you can find the examples of use. Then the main topic of today's presentation, the codependence module and the risk estimator submodule that has tools closely related to the codependence measures. Finally, I will show you where can codependence be applied in MLFinLab package in particular and in general in quantitative finance. And lastly, there will be links to references for those who would like to study some of the topics in more detail. So first, the MLFinLab package. This package exists since 2018 and started as implementation of series of works of Lopez de Prado. That's why throughout this presentation, you will see a lot of links and references to his work. But recently, we've also implemented a few techniques from elite and peer-reviewed journals. Our package is available on PyPy and can be easily installed and used via pip install MLFinLab. It is an open source Python package. Here is a link to our main repository, and you can see the code. Maybe you will have some propositions, and we're happy to see them and to adjust our code to them. Currently, we're the top 5th algorithmic trading package on GitHub, and we're still growing. We encourage you to have a look at our Read the Docs site to introduce yourself to our functionality and have a deeper understanding of our models and our modules. We also have a Slack channel that is available to each of our Patreon supporters of any level. If you would like to find a community of fellow researchers to discuss papers with or to do some pet projects with, we encourage you to join it. So here are the main or the all MLFinLab modules that are currently available. We are still growing, so more modules will come in the future. Generally, I'll describe them right now. So starting from feature engineering that allows one to create various bars, not only the standard time bars, but also the volume and dollar bars, etc. Also detect shifts in market regimes and create multiple features. Codependence is the module that I'll describe in more detail today in this presentation, and you will have a deep understanding of what it contains. Labeling allows to label data to further use it in training or testing models. Modeling allows to sample data for better properties of it. Clustering allows one to cluster a data based on the codependence, or as in the original algorithm, correlation covariance matrix. The backtest overfitting is a rather interesting module that allows, apart from measuring standard characteristics of returns, also adjust Sharpe ratios described in papers to the real, so to say, ones. So adjusting them to multiple testing, because in many papers, researchers use the same model multiple times on the same data set to get better results, and they not take into account the multiple testing. The portfolio optimization module is one of our mostly used ones. And apart from standard risk metrics, etc., it contains multiple portfolio optimization methods, starting from the standard ones proposed by Markowitz, such as the mean variance optimization and the CLA algorithm. And finishing with the novel approaches such as HRP, hierarchical risk parity, or the HERC or the NCO algorithms. Finally, the online portfolio selection module was built throughout the last 2 months by one of our researchers and contains widely used benchmarks to compare the portfolio performance to. The key here is that it's an online algorithm set, so they are pretty efficient and run fast on big chunks of data. Examples of use of many R functions, nearly all of them, are available in the research repository, and here's the link to it. It contains more than, right now, 45 notebooks in Jupyter. Each notebook ideally includes the beginning, the main part, and the conclusion, and a bunch of theory describing the functionality. So if you would like to try our functions hands-on or decide whether you can use them in your particular problem, I encourage you to have a look at these research notebooks. The main topic of today's presentation is the codependence module, and it's basically the idea of measuring the dependence or association between two random variables. And in quantitative finance, those would be assets or any other financial tools. Today's presentation application is going to be based mainly on the quantitative finance, but the tools that I'm going to be presenting are also applicable to other areas of science and machine learning. So I'm going to be briefly covering the Pearson's correlation, the distance correlation, the angular distance, the information theoretic codependence, and the GPR and GNPR distances. First, Pearson correlation is a widely used measure for measuring codependency between elements. However, it has its caveats that are widely known. First one being that it measures only linear dependence between elements and neglects the nonlinear relationships. In this basic example on the graph here, you can see that although variable 1 and 2 are dependent nonlinearly, the Pearson's correlation fails to grasp this codependence. Also, Pearson's codependence is highly influenced by outliers, and these two elements make it rather a flawed measure of financial codependence according to Lopez de Prado. Also, Pearson's correlation is typically meaningless unless it's used to variables that are distributed normally. It's worth noting that this first part of the presentation, which is codependence module, is based on the presentation by Lopez de Prado, and it's the first link in the references if you would like to check the original work. Now to the distance correlation. The distance correlation is a generalization for Pearson's correlation that was introduced in the year 2005 by Gabor Shekli. It has its own set of interesting properties, and here on the graph on the right you can see the distance correlation of different data sets. For example, on the second line you can see that where Pearson's correlation would actually show first a high positive dependence, then going to the zero correlation, and then slightly going to a high negative correlation. The distance correlation sees that there is a strong codependence between variables. And on the third and the fourth line of examples, you can see that where Pearson's correlation would show around zero correlation between elements, distance correlation can actually see the nonlinear dependencies in random variables. So the properties, first being that distance correlation is non-negative and ranges from 0 to 1, so unable to measure, so to say, negative correlations between elements, as Pearson's correlation does. The second would be that it implies the independency of random variables, which means that if the distance correlation is 0, it means that the variables are independent and backwards. So this measure can be used to determine or test the independency of random variables. Unfortunately, it's rather computationally expensive at O big N squared versus the O big N for Pearson's correlation. And that's because to calculate Pearson's correlation, we only need to allocate in the memory the N observations that we have. And from then we can calculate the Pearson's correlation. Well, for distance correlation, we actually need to calculate the differences between each pair of observations, therefore creating a matrix size n by n. So it's more space complex at O big N squared, which is a problem for big data sets. But in some applications, you may not need to actually calculate distance correlation for the whole data set. And in some applications, you can use a rolling window approach that neglects this problem. Another property is the distance correlation has its analogs for ordinary moments. So distance variance, distance standard deviation, and distance covariance, which makes it an easier item to use where previously the Pearson's correlation was used and to test it around. Now let's move to the angular distance. First, I'm gonna remind you of a definition of a metric that came from a field of topology. So a metric is a function on a set, and it has an interesting property that it induces an intuitive topology on a set. Why do we want this property? Well, this property is specifically interesting and is meaningful for clustering applications. Therefore, we can use the notions of proximity and similarity. It's worth noting that not only in clustering applications would we need this property, as novel portfolio optimization techniques are relying on clustering as one of their steps. So having a metric defining the distance between random elements or assets, financial instruments, is a good property to have. So a function on a set is a metric if it follows four properties. First being the non-negativity, which means that a function from two elements is more or equal than zero. Then identity of undiscernibles, which is if the function of two elements is zero, this means that these elements are equal. Symmetry, so interchanging the order of elements in a function wouldn't change the value of the function. And the subadditivity, which is available on this slide right here. Unfortunately, the Pearson's correlation is not a metric, as it doesn't comply the non-negativity and the subadditivity property. There is a problem with this, as stated in the book of Lopez de Prado, which is if we have a difference at two sets of correlations, one being 0.9 and another being 1.0, and the second being the difference of 0.1 and 0.2 correlations. The difference between those correlations are the same, although the former involves a greater difference in terms of codependence. So, therefore, metrics based on Pearson's correlation were proposed. And we're going to be looking at three of those metrics. Of course, there are multiple of them. First being the angular distance, then the absolute angular distance, and finally the squared angular distance. For a proof that these functions are indeed metrics, you can visit a work of Lopez de Prado from 2016 that is linked in the references. On the right side of the presentation, you can see three graphs that show how these angular distances transfer the Pearson's correlation from a range from -1 to +1 to a range of a distance from 0 to 1. And angular distance has its own nature of behavior, but the absolute and the squared angular distance have a rather different behavior. So the first one treats highly negative correlated elements as very distant, and the last two treat highly negative correlated elements as very, very similar. So it says that the distance between them is actually close to zero. Why would we need such a property? Well, it all relates to building portfolios. Generally, we can divide the tasks of building portfolios between the long-only portfolio problems and the long-short portfolio problems. In the long-only portfolios, we're only allowed to go long or to purchase a certain set of assets, and we're not able to sell elements if we don't have them on hand. So we can't use the short mechanism. Whereas for the long-short portfolios, we can actually use the short mechanism. So borrow a certain set of assets and then sell it. So basically sell them if we don't have these assets on hand. For the long-only portfolios, it would make sense to use the angular distance, because if we have two elements that have high negative correlations between them, actually buying first and buying the second one would have drastically different performance or result on our portfolio. So if one would go up, other is likely to go down, which would cause different effect on our portfolio. But if we have a pair of highly negative correlated elements and we are solving a long-short portfolio problem, we can actually go long on one element and go short on another element. And if one of them goes up, another one would go down, but since we have shortened it, it would also increase in price, so to say. Therefore, if we're solving the long-short portfolio, it makes sense to treat highly negative correlated elements as being similar or having small distance between them. Now to the information theoretic codependence measures. This is a whole family of measures that is based on the information theory by Shannon, which is based on the understanding of an entropy. An entropy can be described as a measure of uncertainty of a random element. Unfortunately, it's only finite for discrete random variables. And in real life and in financial applications, we often have continuous random variables. Therefore, we need to discretize our observations, or basically to divide them by a certain set of bins. And then we can estimate the probability of an element being inside a certain bin. However, there is a problem to that approach, because depending on the number of bins that we would choose, we would have different estimators of these measures. There is, however, a workaround through it. Many researchers proposed an optimal number of bins for a certain set of problems. For references to those works, you can, for example, see the latest book of Lopez de Prado. But if one would not like to rely on the number of bins, you can read a recent blog post by Dr. Gautier Marty, which states that actually one can use copulas to estimate these measures. Why would one use copulas? Well, first, copulas have a support from 0 to 1, whereas a random variable in theory has an infinite support from -infinity to +infinity. This therefore makes the estimation more numerically stable, one. And the second, and by following an example shown in that blog post, actually, if we have a smaller set of observations or a random variables that have heavier tails, the estimation of mutual information based on copulas show better results. So you can see on this graph, also taken from the presentation of Lopez de Prado, how the entropy of element X, element Y are related. Here you can see where the joint entropy, the conditional entropy, the mutual information, and the variation of information are. So the mutual information can be interpreted as a decrease in uncertainty of element X if we know the value of element Y. And here it's an interception between the entropy of element X and element Y. It is not, however, a metric, as this doesn't comply to the subadditivity property. The variation of information can be interpreted as the uncertainty that we expect from element X if we know the value of element Y. And this is a true metric that can be used for clustering applications or the portfolio optimization applications that require clustering as one of the steps of the algorithm. Now to the GPR and the GNPR distances. So the GPR is a generic parametric representation, and the GNPR is a generic non-parametric representation distance. Basically, the GPR applies to Gaussian distributed variables, and the GNPR applies to any IID random variables. This measure was introduced by Gautier-Marty, and it allows to discriminate variables on distribution and dependence. Generally, according to author, we can divide distances between two families. First being the distributional distances. So we are looking at the distribution of element X and element Y, and we compare the distributions. Another would be the dependence distances. So measuring the codependence between elements, be that distance correlation or advanced copula-based dependence metrics. Showing this on an example, also proposed by author, say we have two perfectly correlated random variables, but one has heavier tails than another. And although they are highly positively correlated, in terms of risk, they are quite different because one has heavier tails than another. The GPR and the GNPR distances take parameter theta that ranges from 0 to 1, depending on the proportion of the distributional distance and the dependence distance that we're measuring. So for theta 1, we're measuring the distribution information. For theta 0, we're measuring the distributional information. For theta 1, we're measuring the dependence information. And for any theta from 0 to 1, we're having a mix of this information. This is an example that would show why this distance in particular is meaningful and can be used in many applications. So from the second column of graphs, so to say, we have 5 clusters of random variables, random elements. The elements within the cluster I are highly correlated, and they have lower correlation with elements outside the cluster, which can be seen in these two graphs. Also, we have these five clusters. Within each clusters, the elements are also subdivided between two subclusters. First of them being distributed by a Laplace distribution, and another through T distribution. The T distribution has heavier tails than the Laplace distribution, but both of them in this example have the same mean and the same standard deviation. So when applying the GPR, we fail to see all 10 original clusters, but when actually applying GNPR, we can see the 10 original clusters. So apart from dividing random elements based on the codependence, we can also see that inside they're different based on the distribution. Also, so now we've finished with the codependence module. It's worth noting that although all the above tools are defined for 2 random elements, we actually have a function called codependence matrix function that allows one to feed a whole data frame of observation and get as an output a codependence matrix, which would show codependence, the chosen tool of codependence, between each pair of elements, which can be pretty handy for your research purposes. Now for the risk estimator submodule. This is a part of portfolio optimization module, which has tools that are closely related both to codependence and to portfolio optimization. These tools are applied to covariation or correlation, matrices or measures, and are aimed to tackle the caveats that they have. So that would be poor numerical properties or high influence by outliers. So I'm going to cover here the minimum covariance determinant, the covariance estimator with shrinkage, the semi-covariance matrix, and the denoising and detoning covariance matrix. So first, the minimum covariance determinant. What is the goal of this tool? The goal is to adjust to sensitivity of the outliers of the covariance and the correlation. This estimator was introduced by Barziy, and the main idea here is we take a subset of observations that we assume are not outliers and calculate covariance based on them. Later, we adjust this covariance to decrease in the size of our set. This can be seen on the first graph on the slide, where we can see a slight difference when using the classical covariance estimator and the robust covariance estimator, in this example being a minimum covariance determinant. On the right graph, you can see an example reproduced from code snippet from scikit-learn. And here, an amount of contamination in percentage is the percentage of outliers in a data set. So with the increase of outliers, you can see that the full data set mean and the full data set empirical covariance are different from the pure data set mean. But when we're using the robust location and robust covariance, in this example, the minimum covariance determinant, the estimators of the covariance, well, the estimators of the mean and the covariance are very, very close to the pure dataset mean and covariance. Next, the covariance estimated with shrinkage. What is the goal here? The goal here is to have better numerical properties for the covariance estimator. What I mean by that? In some applications, it's crucial to have a covariance matrix to be, so it would be crucial for it to be invertible. In some applications, such as portfolio optimization using the standard methods proposed by Markowitz, such as mean variance optimization or the CLA, if we're having, however, a high difference between the smallest and the largest eigenvalue or a big condition number of a matrix, this becomes a problem. And we may face a problem that we either can't invert a covariance matrix, or even if we could invert it, it would have poor numerical properties and be unstable. By instability, I mean here that the slight changes in the original covariance matrix would drastically change the inverted covariance matrix and therefore drastically change the weights of elements in our portfolio. First problem, that we would basically have higher transaction costs from that portfolio on rebalancing. The second being that it wouldn't uncover the, so to say, deep dependencies between elements because it's highly influenced by small changes in the original observations. A way to do it is to shrink the covariance matrix. Using the formula available on slide, this is how it's done. So we're basically having a parameter alpha, a shrinkage parameter, and we're multiplying 1 minus alpha on previous covariance matrix, and alpha multiplied by average element on a trace of original covariance matrix placed on the main diagonal. Using the MLFinLab package, user can use 3 shrinkage methods, first being basic, second being Ledoux-Wolf, and the third being OAS estimate. Basic would require for a user to specify the shrinkage parameter alpha. Ledoux-Wolf would be applicable to any distribution of random variable, and OAS works better for the Gaussian distributed random variables. It's worth noting that the problem of inverting the covariance matrix is especially crucial for big data sets. So if one has a set of 5 or 10 elements, there would be no problem with inverting the covariance matrix. But if one would like to use the mean variance algorithm on the S&P 500, that would be a problem because this is where we would have instability in the data. Next, the semi-covariance matrix. This is an interesting tool which was mentioned back in the works by Markowitz. However, it's not widely used right now. What's the main idea here? The main idea is to measure the downside volatility of a portfolio. So basically, only the covariance of observations that are below a certain threshold. Using the given formula right here, you can set a threshold B to anyone, to any threshold. Standard being, for example, 0. So we would measure covariance between observations that are below 0. Why would we need this specific tool? Because we might not be interested in decreasing the overall volatility of our variable, say, portfolio, because we may not be interested in decreasing or stabilizing the high spikes in return if they're positive returns, but we may be interested in stabilizing or making more or less constant the negative returns or eliminating the high negative spikes in our returns. One of the examples where this tool is used, I found in a research paper by Selective, a Germany-based index provider, that shows that when optimizing an index by minimum volatility, one would achieve a light blue performance of a portfolio. But when optimizing by downside volatility, one could get a dark blue performance of a portfolio, which gives higher growth of returns without increasing the volatility to a great extent and therefore decreasing the Sharpe ratio. Finally, the last tool in the risk estimator submodule is the denoising and detoning of the covariance matrix. The goal here is exactly the same as with shrinkage, so to have better numerical properties of the covariance matrix. But if in the shrinkage we didn't take into account which eigenvalues are we shrinking, here we are particularly interested in shrinking and changing only the eigenvalues and the associated eigenvectors that are related to noise and not to signal. This tool in more detail is described in the latest book by Lopez de Prado. So in the first graph taken from his book right here, you can see that the empirical observations or the empirical eigenvalues are generally following this structure where we have a spike of eigenvalues in the beginning of the possible range of eigenvalues, and then a few observations that are having higher values down the line. So the idea here is to fit a Martian-Copastor distribution over the first spike of eigenvalues. Here, this would be from around 0.3 to 1.2, and therefore determine the maximum theoretical eigenvalue. In this example right here, it would be around 1.2. So we would only change the eigenvalues below this maximum theoretical eigenvalue, and we would not change the elements that are above it, because the elements in this example between 0.3 and 1.2 are related to noise, and the eigenvalues that have higher values are associated with signal. On the right graph, you can see how we've changed the eigenfunction. So we are taking the average value of the eigenvalues that are in this first spike. Therefore, the original eigenfunction had a big difference between the highest and the lowest eigenvalue. But when we took the average of the noise-related eigenvalues, we have a smaller difference between the highest and the lowest eigenvalues. So we got better numerical properties and changed only the noise-related eigenvalues. The detoning is an adjustment to the already denoised covariance matrix, and it is based on removing the eigenvector, one or multiple associated with market component. So as author describes it, it's similar to removing a loud tone that prevents us to hear other sounds, because market components would have big influence on the covariance matrix. When removing them, however, it would help the clustering algorithms to see the codependence between elements, as we've removed this loud tone. But after the detoning, the resulting covariance matrix wouldn't be applicable to the standard portfolio optimization methods, such as mean variance optimization, since it would be a singular matrix. We've basically removed one or more eigenvector and eigenvalues. But this is a good tool to be used for clustering-based portfolio optimization methods or in just clustering. Now to the applications of these codependence tools in MLFinLab and quantitative finance in general. First would be the optimal number of clusters algorithm that in its original version allows to cluster elements based on the correlation/covariance matrix. But basically any codependence matrix can be fed into it, so we can see alternative clustering of algorithms based on various codependencies. Next would be the portfolio optimization, where the mean variance and the CLA would benefit from denoising and detoning and shrinkage, and the robust estimator of the covariance, as it would adjust to the caveats of the Pearson's correlation that is used in this portfolio optimization algorithms. For the HRP and the HERC, one would benefit from using alternative codependence measures described in the codependence module part of this presentation, so the variation of information, distance correlation, and etc. Finally, I would like to tell you about an interesting estimator tool for codependency measurement, the theory-implied correlation. Why am I saying it's interesting? Because whereas all the previous methods and tools that I was presenting relied on only using the previous data, so empirical observations to estimate the codependence between elements, this particular tool presented in the work of Lopez de Prado from 2019 allows one to combine the empirical data with the theoretical structure. So in the original example, it's a combination of the empirical correlation matrix with the GICS hierarchical structure of stocks, which divides stocks by sectors, industry groups, industries, and sub-industries. This particular approach would allow to denoise the matrix, but based on the given theoretical structure of the data. You can also find more explanations on this method in the blog posts of Hudson and Thames, or in the research notebooks that is available on the research repo of MLFinLab. Also worth noting that as a theoretical structure, here can be given not only the GICS, but basically any given structure, because for some assets, for some variables, there may be not a ready structure available to be used. In the original paper, it's also proposed that, for example, a structure can be taken as an output of a machine learning algorithm. So we can give a big chunk of news to analyze to a machine learning algorithm, and it may come up with a custom hierarchical structure that can be used to denoise the empirical correlation matrix. This method allows to combine the backward-looking approach from correlation matrix and a forward-looking theoretical structure. Here are references to the tools that I was using in this presentation. If you would like to study these tools in more detail, the link to the presentation would be available in the description for this video. I encourage you to have a look at our Read the Docs section and our research repository at GitHub to get more understanding about the functionality that MLFinLab package has, and to see if you can find our tools handy and you can use them in your research. If you want to support our package, you can become a Patreon and unlock the access to our Slack channel, where you can find fellow quants to discuss papers with, or maybe to do some projects together with. thank you for your attention and thank you for visiting this presentation. I hope you've learned something new and interesting from it, and I will see you next time. Goodbye.